This video describes an interactive environment for the graphical analysis of spatial data. The members of the development team include Jim Major, Diane Cook, Jürgen Szymanczyk, and Ina Magretskaya. The environment is based on a link between a geographic information system, ArcView, and a dynamic graphics program, XGOBI. The use of a GIS helps to keep the analysis in its proper geographic frame of reference, while the incorporation of dynamic graphical tools provides powerful analysis capabilities. The link has several types that are used for different purposes in the analysis process. This video will present each type of link and give an example of how it is used. The three types of the link are the multivariate link, the variogram cloud link, and the spatial cumulative distribution function, or SCDF link. In the multivariate link, data associated with sampling locations stored in ArcView are passed into XGOBI to be analyzed. This link is used to search for outliers, clusters, or structure in multivariate spatial data. The data set that we will consider first is precipitation sampling sites in the northeastern United States. The data represent quarterly precipitation totals. The precipitation sampling stations in this study are located in 4 states: Maine, New Hampshire, Massachusetts, and Vermont, and range from low-lying areas along the Atlantic coast to the White Mountains of central New Hampshire. When the link is initiated, the multivariate data are passed to XGOBI and the XGOBI window is started up. In a dot plot of elevation, notice that 2 points are located considerably higher than all other points. By displaying an XY plot of the elevations versus the precipitation for the third quarter of 1990, it is clear that the precip for these points is high as well. We can find out where these sites are located using the linked brushing capabilities. Displaying these sites with elevation contours confirms their situation. Erase brushing can be used to delete the highest point so that analysis can continue. We are interested in modeling precipitation in space so that we can predict the value at additional points. We can consider this model, where the precip P at a location S is a function of explanatory variables X at a location S plus a stationary error term. The explanatory variables that might help to explain the variation in the precipitation include the XY coordinates and elevations of the sampling locations. This can be explored using the XY plot and brushing capabilities in XGOBI. As an example, the precipitation for the third quarter of 1990 is plotted versus the X coordinate, and the sampling locations are displayed on a background of elevations. Notice again that the land rises steadily as one moves away from the Atlantic Ocean until it reaches the top of the White Mountains in central New Hampshire. If a horizontal brush is passed over the precipitation values from high to low, it becomes clear that, in general, the values decrease as one gets closer to the ocean. That is, the precipitation values are a function of distance from the ocean. This knowledge can help to provide a beginning point for detrending the precipitations for subsequent variogram analysis and spatial prediction. The variogram cloud link is used to make initial assessments of spatial dependence, to locate spatial outliers or pockets of non-stationarity, and to explore for possible anisotropic variation. In this link, as the data are passed from ArcView into XGobi, several variables are calculated for each pair of sampling locations, including the distance between each pair of locations, the angle between each pair of locations, and also the sine and cosine of the angle, and several variables that are labeled Gij, read gamma ij. For each pair of locations, gamma ij is equal to the square root of the absolute value of the difference between variable I at one location and variable j at the other. The variogram cloud is generated by plotting a gamma value, for example, gamma 11, labeled G_11, versus the distance, labeled D. If the process exhibits strong spatial dependence, then the variation in the gamma values will increase as the distance increases. In this example, gamma 11 is plotted, which is the precipitation for the third quarter of 1990. It looks as though there is spatial dependence, with the gammas increasing in variability out to a distance of approximately 30 kilometers. To check for spatial outliers, or pockets of non-stationarity, we brush the points in the variogram cloud plot. When several points that have high gamma values originate at a single sampling site, that location is brushed in the map view. This shows all pairs of locations to which that location contributes. Consistently high values can indicate problems with the data or a possible area of non-stationarity. Here there are two sampling locations that appear in several high gamma values. The one on the right is brushed in green, and the one on the left is brushed in pink. The largest observed precipitation value was at the location brushed in pink, and the second largest was at the location brushed in green. In the variogram cloud plot, however, the green points are generally higher than the pink points, indicating that, in a spatial sense, this value is more unusual. The value of the point on the left is, at least in part, explained by its relatively high elevation. This analysis might call for additional work to explain the value on the right. Variation of some processes depends on the angle as well as the distance between locations. In order to explore this anisotropic variation, the XGobi window can be cloned and the sine of the angle can be plotted against the cosine of the angle. This plot appears as a circle that corresponds to the angle formed between each pair of locations. This circle can be brushed in order to explore variation in different directions. When the angles corresponding to the northeast-southwest direction are brushed in pink and the southeast-northwest direction are brushed in green, it appears that, on average, the values in the southeast-northwest direction are higher than those in the northeast-southwest direction. This makes sense because precipitation will tend to be more similar as one moves parallel to the coast and change more dramatically as one moves from the coast inland. The SCDF link allows spatial cumulative distribution functions to be predicted and visualized for user-defined regions. In this example, we will predict and visualize SCDFs of the crown defoliation index for deciduous trees in the spatial domain of interest. The crown defoliation index is an ecological index that represents tree crown health response to stressors in the environment. The data viewed in this example include both observed values collected at sampling locations in the northeastern U.S., as well as additional values that were predicted from the observed data using a spatial statistical model. The definition of the theoretical SCDF is given here. In its essence, the SCDF is the proportion of area in the spatial domain of interest, denoted B0, for which the value of the random field being considered is less than a cutoff value, denoted little z. The SCDF link uses a discrete version of this formula to predict the SCDF from existing data over user-specified regions. When the link is started, the SCDF is calculated for the entire region. The user can then define subregions over which the SCDF will be calculated. In this case, we will compare the SCDFs for two regions, one corresponding to the portion of the study area that falls in the states of New Hampshire and Massachusetts, and the other corresponding to the portion of the study area that falls in the state of Maine. Up to 10 regions can be specified. The predicted SCDFs for the two delineated regions seem to indicate that the values of the crown defoliation index are higher for the region in the state of Maine than the other region. Linked brushing is available in both windows. Brushing a spatial region in the map window, identify those points in the SCDF. When the locations in northern New Hampshire are brushed, it can be seen that they fall in the mid to upper portion of the SCDF curve for that region. Brushing can also be done in the XGOBI window. For example, if cutoff values have been determined a priori that define health classes based on the index, those classes can be brushed using a vertical brush. Here, the values of 15 and above are brushed. Using a horizontal brush, quantiles of the index can be identified. Here, the top 10% of the values are brushed. The tools presented in this video represent an environment for the graphical analysis of spatial data. The integration of dynamic graphical tools with a GIS helped to keep the analysis in its geographic frame of reference while providing the user with powerful graphical analysis functionality.